This video is going to be about barometers, manometers, and converting pressure units. A barometer is used to measure outside atmospheric pressure, and here's how it works. A glass column is filled with mercury, flipped over into a pool of mercury, and really the width of the column doesn't really make any difference. And as the mercury falls, there's going to be a vacuum that's created up here. What's supporting the mercury in that column is the outer atmospheric pressure. And at standard atmospheric pressure, this column of mercury will be 760 millimeters tall. On a high pressure day, there'll be a greater atmospheric pressure pushing down on that mercury, which causes the mercury level to rise. And so we read a higher mercury level than 760 millimeters of mercury. But on low pressure days, there's not as much pressure pushing down on the mercury, so the mercury falls. If you were to take a barometer or mercury barometer out in outer space, it would be, basically useless. There is no atmospheric pressure out there, so all of the mercury would just fall right out. Because mercury is pretty toxic, I don't think mercury barometers are used that much anymore, but I think there is utility in just understanding how they work, because we often use this unit, millimeters of mercury, when we talk about pressure units, and that's where the unit comes from. While barometers measure atmospheric pressure, manometers measure confined gas pressure. Here's a picture of a manometer. Inside here there's a confined gas and there's a valve holding that gas in there. And this is just a U-tube, like a glass U-tube that's open to the atmosphere, and the black stuff in here is mercury. So when this valve is opened, gas particles are going to come down through this tube and they're going to bounce or create a pressure against the surface of this mercury. The atmosphere, those gas molecules there, are also going to exert a pressure on top of the mercury on the right-hand side. And if there's a pressure differential between the confined gas and the atmospheric pressure, there's going to be a height differential between the two. And that height difference basically just tells you the difference in pressure between the confined gas and the atmospheric pressure. In this picture, we see this difference in height between the confined gas and the atmospheric pressure being measured as 22 millimeters. The trapped gas is not pushing as hard on that mercury as the atmosphere is. So what we do is we take the atmospheric pressure, in this case measured to be 748 millimeters of mercury, we subtract the height difference to get the pressure of the confined gas. The confined gas is A, shows the highest gas pressure. It's pushing the mercury down harder on this left-hand side. In container C, we have the confined gas that shows the lowest gas pressure. It's not pushing down on the mercury nearly as hard. And the pressure of gas B in the confined gas is exactly the same as the atmosphere. In this question, we're asked to determine the pressure of the confined gas, and we know that the air pressure is 752 millimeters of mercury, and we know that this height difference is 42 millimeters. In this case, the pressure of the gas will equal to the pressure of the atmosphere plus the difference in height between the two mercury levels, because the confined gas is pushing down harder on the surface of the mercury than the atmosphere. So when we add the two pressures together, we get a confined gas pressure of 794 millimeters of mercury. In this question, we read the height on the left side is 6 millimeters, and the height of the mercury on the right side is 26 millimeters, and we're asked to find the pressure of gas A. We also know the pressure of the atmosphere is 690 millimeters of mercury. So once again, the pressure of the confined gas is going to be greater than the atmospheric pressure. It'll be the atmospheric pressure plus the height difference, because the pressure of the confined gas is pushing harder on the mercury. Here's our final answer. I've taken the pressure of the atmosphere, added the difference in height, 26 minus 6 is 20, and gotten a final gas pressure of 710 millimeters of mercury. There are a variety of different units we can use for pressure. We've already been introduced to the millimeters of mercury. A millimeter of mercury is equivalent to a torr. And all of these different units are equivalent to one another. So 760 millimeters of mercury is equivalent to an atmosphere, abbreviation ATM, which is equivalent to 14.7 pounds per square inch, which is the English system of measuring pressure, which is equivalent to 101.325 kilopascals. That would be the metric unit for pressure, a pascal. So I just need you to be able to convert between these units. In this sample problem, we're converting 0.75 atmospheres to millimeters of mercury. It's worth mentioning that the unit conversions are on the back of your periodic table. I think they're on the right-hand side. So here I've taken the given value of 0.75 atmospheres and I've multiplied it by my conversion factor. I know 1 atmosphere is equivalent to 760 millimeters of mercury, so I'll simply multiply 0.75 times 760 divided by 1 to get my answer. Rounded to two significant figures, I get 570 millimeters of mercury. I'm not going to solve this problem, but I wanted to just bring your attention to the fact that when you do your homework, you'll see some problems similar to this, where you're given a manometer, you have to determine the pressure of the confined gas, but your atmospheric pressure is given in units of kilopascals. You'll need to change those to millimeters of mercury so that you can either then add or subtract as needed the height differential between the left and right hand side of this manometer. So just make sure you're working in the same units when you're dealing with these manometer problems and use unit conversions as necessary. I think that's it.